In the last couple of videos, we talked about power functions and their basic properties, and we graphed a few using our transformations. Now let's talk about some other properties of polynomial functions. So if we look at this graph here on the right, you can see that at every x-intercept, and remember the x-intercepts are where it crosses the x-axis or touches, points on the x-axis anyway. The x-intercept, the graph either does one of two things. Either it touches the x-axis or it crosses the x-axis. So as you can see here, we have three of the intercepts. It crosses the axis, and at one, it just touches the x-axis. So consequently, between consecutive x-intercepts, the graph is either above or below the x-axis. So you can see between these x-intercepts, it's above, and then between the second and third x-intercept, it's below, and between the third and the fourth, it's below. If we factor a polynomial function completely, it's easy to locate the x-intercepts by solving f of x equals 0 using the zero product property. Which, remember, the zero product property says if a times b equals 0, then a equals 0 or b equals 0. So for example, if we have f of x equals x minus 1 times x plus 5 squared, we can see that the zeros of the function are x equals 1 and x equals negative 5. And we get those by doing x minus 1 equals 0. So if we add 1 to both sides, we get x equals 1. Or we have x plus 5 equals 0. And so by subtracting 5 from both sides, we end up with x equals negative 5. So based on these facts here, the following four statements are equivalent, meaning that they all mean the same thing. So these are very important because we're going to be using these a lot in the rest of this section and in section 5.5. So one of the statements is R is a real zero of a polynomial function f. That means the same thing as R is an x-intercept of the graph of f. It also means that x minus R is a factor of f. And it also means that R is a solution to the equation f of x equals 0. So let's see how this works in practice. This first one should be familiar because it's just a quadratic, and we know to solve quadratics, we take the function and set it equal to 0. And then we factor. So we have x plus 3 times x minus 1 here. So either x plus 3 equals 0 or x minus 1 equals 0. So we can subtract 3 on the first equation, add 1 to both sides on the second equation, and we get x equals negative 3 or x equals positive 1. So that's how it works when we have to factor ourselves. Sometimes, though, we don't have to factor. They give it to us in factored form. That's the case on B. So on B, it's already factored. So we can write x plus 1 equals 0 if we set the whole function equal to 0, or x minus 2 equals 0. Now it doesn't matter that these are raised to exponents, right? Technically, we could write it out as f of x is 5 times x plus 1 times another x plus 1 times an x minus 2 times x minus 2 times another x minus 2. But since, we have two x plus 1s, they're going to result in the same solution, so we only have to solve once. So if we do that, just finish solving these equations for for x, we have x equals negative 1 or x equals positive 2. So that is just finding the zeros. What if they give us the zeros and tell us to find a polynomial of degree 3? Well, this is where we use this statement right here. If r is a real zero of a polynomial function, then x minus r is a factor. So if we use numbers 1 and 3 from above, we can say f of x equals x minus a negative 4 times x minus a negative 2 times x minus a positive 3. Degree 3 means we'll only have 3 factors. So we can just clean this up now, and our final answer is f of x equals x plus 4 times x plus 2 times x minus 3. And we could multiply all that out, but we don't have to. So, a couple other things. If r is a zero of a polynomial, and the exponent of the factor that produced the root is m, then we say r has a multiplicity of m. And we'll talk about that more in the next video.